Good day. My name is Zhao. I'm an assistant professor in Pitt with the Department of Mechanical Engineering. So today my topic is achieving reliable metal additive manufacturing via online control-oriented machine learning of in-situ optical profilometry data. This is especially presented to MDS-Rely Center kickoff meeting. Congratulations to the new center. And I'm glad and honored to have this opportunity to join this meeting in the center. Thank you. This is a brief introduction about myself. My main research area is on advanced manufacturing, currently focusing on additive manufacturing. And one research thrust is to integrate measurement science and control technology into these advanced manufacturing technologies. My research lab is ZXY Intelligent Precision Additive Manufacturing Laboratory. A little bit background about this proposed project on metal additive manufacturing and reliability. So additive manufacturing or 3D printing, as you already know, is a high-value technology that can fabricate parts using converting a solid object model into a physical object layer by layer. However, due to the lack of established qualification methods, especially due to a scarcity of online process monitoring and control methods, AM technologies are immature and causing uncertainties and increased risks for involved stakeholders. So real-time measurements for the powder bed fusion process-based additive manufacturing, for example, is the result to detect those defects. So in situ, however, in situ layer-wise 3D topography measurements is challenging due to the scarcity of applicable sensor systems. Those systems cannot be fulfilled by existing commercial profilometers or microscopes because they have very short working distance and they are unable to fit in a typical AM machine such as a laser powder bed fusion process, LPBF process machine. So here we are going to use a lab designed fringe projection profilometry, for short FPP technique, to measure the powder bed surface topographies in situ and in real time. Because this FPP technique is very flexible and can measure at a distance without intruding into a specific machine. And this is very compatible with those additive manufacturing printers. And I will mature a lab designed in situ FPP system, fringe projection profilometry, that can offer detailed knowledge about the 3D surface topography by developing a machine learning-based sensor data analytics. And the developed machine learning method will render the FPP-based in situ monitoring system a capability of automatically and intelligently detecting critical defects, which is crucial to the subsequent development of an in-process defects repair method for process improvement and quality assurance. So this is a picture showing our current in situ monitoring system. My research team at Pitt has been developing this system, which consists two subsystems. One is the let me show. One is this on-axis multiple monitoring system. This is outside the scope of the proposed work here. I will focus on introducing the subsystem on the off-axis. So we have set up this off-axis fringe projection system on top of the EOS 290 commercial laser powder bed fusion process system at Pitt. So this, the purpose of doing the off-axis fringe projection profilometry is to measure the surface topographies of the powder bed layer by layer. So, and we can estimate the thickness in real time of the printed parts. We have performed some preliminary experiments and the data acquisition and the data analysis. Some results are shown here. For example, we printed a set of fatigue bars. Then we can monitor. So you can see from the images here, our sensor is the camera from the fringe projection system and captures images which is encoded with the height information. And we developed a sensor model and a sensor data analytics method, and also we perform the sensor calibration to analyze this raw camera data and convert this data into the height profile of the powder bed. So what we need to do with these measurement results is to understand which area of the defects are critical. So as you already see from this measurement results here, we can measure the thickness profile of the surface of the powder bed and the printed area. However, how to tell which area of the defects and what kind of which defects are significant and require subsequent correction actions to prevent catastrophic defects in the final parts. This research area of classifying the defects based on the control purpose is not well established yet. This is actually a significant research gap. So currently, the common practice is to use machine learning to classify the defects based on the size or morphology of those the shapes of the defects. But some of the, generally speaking, maybe say people can easily say big defects indicate significant areas that needs in-process remedy strategies, right, to fix those defects on the fly. However, it's not necessarily like that because research found that those identified defects, some of them can heal themselves especially during the subsequent printing process. So we need to understand the defects and categorize those defects from the perspective of control and to understand the defects evolution throughout the printing process. So the value proposition of doing this defect classification from the control purpose, from the control perspective, is to avoid over corrections of those defects. So we don't want to overcorrect all those defects, which is time consuming and effort taking. And so by kind of clearly identify this differentiate these critical defects from those non-critical defects, we can improve the control efficiency, especially in real-time fashion. Time is very important. And also, when we say overcorrection, may cause some new defects if we overcorrect some old defects. So if this research is successful, I think this fills the gap of addressing those defects identification for meaningful control practice. The proposed project, the research impact, I would say, just wrapping up what I just introduced, based on the preliminary results, we propose a research initiative for control-oriented defect triage, which will fill the gap in classifying the defects as critical or non-critical from the quality control perspective. And the objective of this proposal is to develop an online defects inspection technology via a combination of in-situ surface topography and sensor data mining for rapidly and accurately detecting critical layer surface anomalies, such as dents and bumps that would induce severe defects in as printed metallic parts, and thereby we can develop in-process remedy strategies during the printing process. Expected outcomes include in-situ optical profilometry sensor data and measurement results of layer-wide surface height map, and ex-situ characterization of those fabricated parts such as microscopy and micro CT to label those data. Then we will create and train and test the neural network for the machine learning methods to immediately recognize or identify those critical defects based on the in-situ profilometry measurement results. And this is the proposed industry collaboration. I'm open to collaborate with any companies who are interested in metal 3D printing here. So we need your support and help, and also your feedback for this new in-situ monitoring method, and also for some potential feedback control methods later of closed loop technologies. To improve the reliability of metal 3D printing process and the metal 3D printed parts. Okay, so yeah, just welcome to work together. And if you have time and interest, welcome to visit us at ZIP AM at PIT. Thank you. Please take care.